In this video we are going to talk about the differential of a function. Now what this is really about, it goes back to something we did at the very start of this chapter. And what it was to do with is the fact that the tangent to a function approximates the function. And essentially differentials is just a way of writing that down. Can you roughly approximate a function? Now what the differential does is it doesn't help approximate the value of the function, it helps approximate the change in the value of a function. That if you change the input a little bit, how much will the output change? This is what we're looking at. Okay, so we want to get a nice picture going here. So for a differentiable function, a differentiable just means that the graph is smooth. So let's say something like this is a differentiable function. We define, so this dx or delta x, we're going to call it delta x, that's okay. Differentiable functions are locally approximately linear, and what that means is it just looks, the function looks like it's tangent near specific points. So let's say we want to go with, it's difficult to choose which point to choose. Let's take this point here. And we know that near this point, the function looks like it's tangent. Something like that. So that's the tangent. Happy days. So, right, what the hell is going on here? So, this is the point x0. And we're going to move over to x0 plus delta x. Okay. Now this is going to cause a change in the function, the value of the function. Maybe if we come over here, go straight across, whatever you get. This is y0, so this is the value of the function at x0, and go straight over from here. This is what we will call y0 plus delta y. Okay. Right. Because the tangent approximates the function, we can use the tangent to approximate the change in the function. Now, the way this diagram has turned out, it might actually be a little, your picture might be a little more realistic, but for the one I've certainly drawn, you're getting a very bad approximation. I'll explain what that means. So if you make a triangle here, so if your curve is a bit bigger, this will make more sense. Draw a line parallel to the x-axis and then parallel to the y-axis like this. Okay. This little guy here is the differential. Okay. And this basically says, according to the tangent, how much will the function change? And it's it doesn't look like a very good approximation here, because over the same thing, how much has the function actually changes? Delta y, which is far bigger. So just to be clear, this dy is this here. Now if delta x is smaller, this is a better approximation. So as I said, the way, if you draw this, you might actually get a nicer picture. Maybe I'll just draw one here on a separate piece of paper and show how it can look a bit nicer. So I probably had my slope changing too much. So take this thing, take this point, draw the tangent. I really need an axis as well. And so I get here. So this is the differential. Your picture might look a bit more like this, and it approximates the actual change, which we call delta y. And when delta x is smaller, these two things are closer together. In fact, like when delta x is as small as this, these are very close together. So this differential is an approximation of the actual change in y. This picture is a bit of a disaster, so maybe your picture looks a bit more like this. Okay. So what have we got here? The differential, which is dy, estimates the actual change in y due to a change in x from x0 to x0 plus h. For small changes in x, now for here the changes have to be really small for here for the tangent and the curve to actually agree. The differential is okay, we said this. Okay. Now what I want to do is I want to find dy here in terms of data that we know. And the way it works is because the tangent here, is a line, and we've got a kind of a rise over run situation because we've got dy and we've got delta x, we can calculate the slope of the tangent. So I'm just going to write slope of tangent. I'm just going to write slope is equal to the rise over the run. dy is the rise and the run is delta x. And now it should be automatic at this stage. When you hear slope of tangent, you're thinking derivative. So this is the derivative f dashed evaluated at x0. So you end up with this little formula here, dy, which is the tangent approximation for the change in the function, is the derivative evaluated at the point you know about times the change in the input variable delta x. Okay, now this will have uses which we'll see soon. So this is kind of saying that there's a very natural way to understand this, saying the change in y is equal to the rate of change. Now remember, f and y are the same, so this is the rate of change of f or y with respect to x times the change in x. So this is rate of change of y with respect to x times the change in x is equal to the change in y. Perfectly good. So it's like saying something like, okay, imagine that your instantaneous speed is 60 miles per hour. Say it doesn't change that much from 60 miles per hour. Then the change in distance is the speed by time. So say, for example, 40 or 60 miles an hour, by 2 hours ago, 120 miles would be the change in distance, something like this. Now for a function of two variables, you can do something similar with the graph. It's a little bit difficult, but it's a bit easier for me just to say that the differential, the change in the function of two variables, is the sum of the differentials. So the derivative of the function with respect to x times the change in x plus the derivative of the function with respect to y times the change in y. Now, if we look at the top of this page, it's banging on about error analysis. So what the hell has that got to do with anything? We will explain that in the next video in more detail, but the idea would be that x0 is going to be your measurement of something. F of x is a formula that you're putting your measurement into. So measurement, formula, calculation. Now the thing is, when you make a measurement, something that's guaranteed to be there whenever you make a measurement is an error. So the true value is possibly here. And the question is, how would that change your calculation? Because errors in the measurement in measurement lead to errors in calculation. And what we're going to do is we're going to estimate the errors in the calculation using the differential. That's what we're going to do in the next video.